There are more directions in the universe than the ones you know how to name. Up, down, left, right, forward, backward. These feel complete because your body lives inside them. Yet modern physics suggests that space itself may be woven with additional directions, hidden not because they are far away, but because they are folded too small, too subtle, too quiet to notice. If this calm exploration brings you even a moment of wonder or rest, I'm deeply grateful you're here. A gentle like, a soft tap on subscribe, or a quiet word of feedback helps keep these peaceful journeys alive more than you know. Now, we begin with the first question. Part 1. What do we mean by a dimension? A dimension is not a place you travel to, but a direction you can move. Length is one dimension. Add width, and a flat line becomes a surface. Add height, and the surface becomes a volume. This simple idea, quietly mathematical, is the foundation of everything you touch. Yet, physics asks a deeper question. Are these three directions the full story, or merely the ones our senses evolved to survive within? To understand this, it helps to slow down and return to something very basic. Imagine a single point. It has no size, no extension, no direction. It simply exists. Now, allow that point to move in one direction only, back and forth. As it traces that motion, it creates a line. That line is one-dimensional. Every position along it can be described with a single number. There is nowhere else to go. Now imagine that line gaining a second freedom. It can slide sideways, perpendicular to its original direction. As it does, it sweeps out a surface, a flat plane. This is the world of two dimensions. Any location on this surface now requires two numbers to describe it: forward and sideways, length and width. Add one more independent direction, one that rises away from the surface, and suddenly, space gains depth. Volume appears. Objects can pass above and below one another. This is the three-dimensional world your body knows intimately. You live inside it so completely that it feels inevitable, as though space itself could not have been otherwise. But physics reminds us that inevitability is often an illusion born of familiarity. Mathematically, a dimension is simply an independent direction of motion. There is no rule in mathematics that limits this number to 3. In fact, equations remain perfectly consistent whether they describe 3 dimensions, 4, or 10. The question is not whether higher dimensions are allowed, but why we experience only the ones we do. One reason this question feels strange is that your intuition is shaped by survival, not by geometry. Your senses evolved to track falling objects, approaching predators, stable ground. They were never designed to visualize abstract spaces. Just as you cannot directly sense radio waves passing through your body, you may not be equipped to perceive every dimension that exists. To see how limited perception can be, physicists often return to a quiet thought experiment. Imagine a universe with only 2 spatial dimensions, a perfectly flat world like an infinite sheet of paper. The beings living there can move forward and backward, left and right, but never up or down. Height does not exist for them, not even as a concept. In this flat world, creatures would build their science around what they can measure. They would know length and width. They could map their universe completely, or so they would think. Now, imagine you, a 3-dimensional being, passing your finger through their plane. From their perspective, something impossible happens. A point appears out of nowhere, grows into a line, then shrinks and vanishes. They never see your full finger, only the intersection of it with their world. Nothing about this event would violate their physics. It would simply be unexplainable within it. This is one of the gentlest ways physics prepares the mind for higher dimensions, not as exotic destinations, but as directions that exist whether or not a given observer can access them. A higher dimension does not replace the lower ones, it contains them. In your own world, shadows behave this way. A shadow is a 2-dimensional projection of a 3-dimensional object. From the shadow alone, you cannot fully reconstruct the object that cast it. Many different shapes can produce the same outline. Information is lost when dimensions are reduced. Physics quietly wonders if something similar is happening with reality itself. When you describe the position of an object in space, you give 3 numbers, 1 for left and right, 1 for forward and backward, 1 for up and down. These coordinates tell you where something is, but they do not tell you when it is. To do that, you must add another quantity, time. At first, time feels different from space. You cannot pause it or reverse direction. Yet in the early 20th century, Albert Einstein showed that space and time are deeply connected. Events do not happen in space and time separately, but in space-time, a four-dimensional structure where time is treated as another coordinate. This does not mean time is identical to space. Its geometry behaves differently. But it does mean that the universe already requires more than 3 dimensions to describe accurately. Even the GPS signals guiding you rely on this fact, correcting for how motion and gravity alter the flow of time. Once this step is taken, the door to higher dimensions is no longer locked. From a purely mathematical standpoint, adding dimensions often simplifies the laws of physics rather than complicating them. Equations that look tangled in 3 dimensions become elegant when written in higher dimensional space. Symmetries emerge. Relationships clarify. This is one reason physicists take the idea seriously, even when direct evidence is elusive. But mathematics alone is not enough. Physics demands that dimensions have consequences. They must influence what we can measure, even subtly. The challenge is that higher dimensions may be hidden in ways that make their effects extremely faint. One possibility is that extra dimensions are compact, curled up so tightly that they are effectively invisible at human scales. At every point in space you occupy, there could be additional directions, folded in on themselves like tiny loops. You pass through them constantly without ever noticing, the same way an ant walking along a garden hose experiences length, but not the circular direction around the hose's surface. From far away, the hose looks one-dimensional. Up close, it reveals more structure. This idea helps explain why dimensions are not simply counted by observation. The universe may have more structure than your senses can resolve. Just as atoms were once invisible to every human eye, dimensions may exist beyond your natural resolution. There is also a psychological comfort in thinking of dimensions as places you could visit, like rooms or alternate worlds. But physics does not require this imagery. A dimension is not necessarily somewhere else. It can be right here, woven into the fabric of space itself. In fact, every time you move, you are already navigating multiple dimensions. As you sit still, Earth rotates beneath you. As Earth orbits the Sun, your path through space-time curves gently. Even rest is a kind of motion through higher dimensional geometry. This perspective softens the strangeness of the idea. Higher dimensions are not an escape from reality. They are a deeper description of it. And there's a quiet humility in this realization. For most of history, humans assumed that what they could see defined what existed. The air was once invisible and unknown. The microscopic world was once unimaginable. Each time science extended perception, reality did not change. Only our understanding of it did. Dimensions may be another such extension. Whether the universe contains hidden directions beyond the familiar ones remains an open question. Experiments continue. Theories evolve. But the concept itself teaches something important even before it is confirmed. It reminds us that space is not just a stage where events happen. It is an active structure with properties, limits, and possibilities still being uncovered. As you rest and listen, you do not need to visualize these dimensions perfectly. No one truly can. It is enough to let the idea settle gently. That reality may be larger than experience, that the world you move through may be a slice of something more expansive. And as we continue this quiet journey, another question naturally rises. If dimensions are directions of motion, and if more of them might exist, then what happens when we try to imagine a space that goes beyond the familiar 3? And how would such a space actually behave? Part 2. Why time became the 4th dimension. Time feels different from space because you cannot turn around and walk back through it. Yet Einstein showed that time behaves like a dimension, woven together with space into a single structure called spacetime. Movement through space changes how quickly you move through time. Even as you rest, your clock is quietly shaped by motion and gravity, sliding along a 4th axis you cannot see. For most of human history, time was treated as something separate from the world around us. Space was where things happened. Time was when they happened. It flowed forward at a steady pace, the same everywhere, for everyone. This idea felt natural because it matched daily experience. Days followed nights, seasons returned. Clocks ticked in unison, or so it seemed. Isaac Newton formalized this intuition in the 17th century. He described time as absolute, flowing evenly without regard to anything external. In Newton's universe, space was a rigid stage, and time was a universal metronome ticking in the background. The laws of motion unfolded against this fixed framework, calm and predictable. For centuries, this picture worked beautifully. It explained falling apples, orbiting planets, and the graceful arc of projectiles. There was no reason to question it. Time felt reliable, steady, and separate from space, but nature had been keeping a quiet secret. At the end of the 19th century, physicists began to notice something strange about light. No matter how fast an observer moved, light always traveled at the same speed. This defied common sense. If you chase a beam of light, you would expect it to slow relative to you, the way sound does when you move toward or away from it. But experiments showed it never did. To make sense of this, Albert Einstein proposed a radical idea in 1905. Perhaps space and time were not independent after all. Perhaps they adjusted themselves to preserve the speed of light. The consequences were profound. Einstein showed that time could stretch and compress depending on motion. If you move very fast relative to someone else, your clock ticks more slowly than theirs. This is not an illusion or a mechanical flaw. It is a fundamental feature of reality. Time itself changes pace. At first, this sounds abstract, but it has been measured countless times. Atomic clocks flown on airplanes tick differently than identical clocks left on the ground. Satellites orbiting Earth must constantly correct their clocks, or GPS systems would drift by kilometers each day. The technology you rely on quietly confirms that time is not absolute. What makes this possible is the idea of spacetime. Instead of imagining the universe as 3 dimensions of space plus a separate river of time, Einstein combined them into a 4-dimensional structure. Events are not just located somewhere, they are located somewhere and somewhen. Each event has coordinates in spacetime. In this view, time becomes another dimension, though one with unique properties. You can move freely through space, choosing directions. Through time, you move in only one direction, carried forward by causality. Yet, mathematically, time behaves like a coordinate that can stretch, tilt, and curve. To picture this, physicists often use a simple diagram. Imagine space as a flat surface and time as a vertical axis rising upward. An object at rest traces a straight line upward through time. An object in motion traces a slanted path. The faster it moves through space, the less steep its path through time. This is not just a visual metaphor, it reflects a deep truth. There is a trade-off between motion through space and motion through time. The faster you go spatially, the slower you advance temporally. Your total motion through spacetime remains constant. Even now, as you lie still, you are moving through spacetime at the speed of light, not through space, but through time. Motion is unavoidable. Stillness is only a matter of direction. Gravity adds another layer to this story. In 1915, Einstein extended his ideas with the general theory of relativity. Here, gravity is no longer a force pulling objects together. Instead, mass and energy curve spacetime itself. Planets follow curved paths not because they are pulled, but because spacetime tells them how to move. Time is deeply affected by this curvature. Near a massive object, time slows down. A clock on the surface of Earth ticks slightly more slowly than a clock aboard a satellite. A clock near a black hole would slow dramatically. From a distant observer's perspective, it would nearly stop. This effect has been measured with exquisite precision. Modern clocks can detect time dilation over height differences of just a few centimeters. Standing up means your head ages infinitesimally faster than your feet. The difference is tiny, but real. So time is not uniform. It flows at different rates depending on where you are and how you move. There is no single universal now shared by the entire universe. Each observer carries their own slice of time. This realization changes what a dimension means. Time is not merely a parameter that orders events, it is a geometric direction shaped by motion and gravity. It bends, stretches, and connects with space in ways that cannot be separated. Hermann Minkowski, one of Einstein's contemporaries, described this shift with quiet elegance. He said that space by itself and time by itself are doomed to fade away, and only a union of the two preserves an independent reality. Spacetime is that union. Once this framework is accepted, the idea of higher dimensions becomes less alien. We already live in more than three. We simply move through the fourth differently. There's also something deeply calming about this picture. It suggests that the past is not gone in the way we often imagine. In spacetime, past events still exist as locations, just not ones you can reach. The future, too, exists as a set of possible paths shaped by present choices and physical laws. You are not racing through time, you are tracing a path within it. This perspective also reshapes the concept of aging. Aging is not something time does to you, it is the record of the path your body takes through space-time. Different paths accumulate different amounts of time. Astronauts age slightly less than people on Earth. Particles created in the upper atmosphere live longer because they move so fast. These are not philosophical claims, they are experimental facts. Time as a dimension is not about perception, it is about structure, and yet time still feels different. You cannot step sideways into yesterday. You cannot pause tomorrow. This asymmetry is real and remains one of the deepest puzzles in physics. While the laws of motion work almost equally well forward and backward, experience does not. This directionality is known as the arrow of time. It is closely tied to entropy, the tendency of systems to move from order to disorder. While space-time itself allows paths in many directions, the universe's initial conditions give time its forward flow. So time is a dimension, but not a simple one. It has shape, direction, and texture. Understanding this helps prepare the mind for what comes next. If time can be treated as a dimension, woven into geometry, then perhaps other dimensions also exist, behaving in unfamiliar ways. Perhaps they are hidden, not because they are far away, but because their geometry confines them. Time was once invisible as a dimension because no one thought to look at it that way. It took a shift in perspective, not new senses. As you breathe quietly now, remember that you are moving, not rushing, not drifting, but progressing along a fourth direction shared by everything that exists. Every heartbeat marks another step along that axis. And as we continue this calm exploration, another question waits patiently ahead. If time could be revealed as a dimension hidden in plain sight, then what other dimensions might exist beyond perception? And how would a purely spatial fourth dimension behave if it were real? Part 3. Seeing Beyond. Flatland. Imagine a world with only two dimensions, a perfectly flat plane. The beings living there could never perceive height, only shadows and intersections. To them, your three-dimensional body would appear as impossible slices appearing and vanishing. This thought experiment, first explored in the 19th century, helps physicists understand how higher dimensions might exist without being directly visible to us. To begin gently, picture that flat world again. There is no up, no down, only forward, backward, left, and right. Everything that exists lies pressed into a single plane. The inhabitants move freely across it, build structures within it, and develop a complete science based on everything they can observe. Their equations describe distances, angles, and motions perfectly within the limits of their world. From their perspective, the universe is complete. Now imagine a simple experiment. You lift a finger and slowly lower it through their plane. From their point of view, something extraordinary happens. At first, nothing is there. Then, a single point appears. That point grows into a line, changes shape, then shrinks and finally disappears. There is no explanation within their physics for where it came from or where it went. They would not see your finger. They would only see the cross-section of it. This is the essential lesson of Flatland, a concept introduced by mathematician and writer Edwin Abbott in 1884. It was not meant as science fiction, but as a way to stretch intuition, to show how an entire dimension of reality can exist beyond perception without violating any known laws inside the lower dimensional world. For the flat beings, their science is not wrong, it is incomplete. This distinction matters deeply in physics. When we talk about higher dimensions, we are not saying that the universe is broken or illogical. We are suggesting that our perspective may be limited in the same way Flatland's inhabitants are limited. What feels impossible may simply be unseen. In Flatland, shadows behave strangely. A three-dimensional object passing overhead casts shadows that change shape in ways the flat beings cannot predict. The shadows are real. They interact with the world, but their source lies beyond direct observation. Physics asks whether some of the strange phenomena we observe might be similar shadows, projections of higher dimensional processes into our familiar three-dimensional space. This is not speculation for its own sake. It is a method of reasoning used repeatedly in science. When something behaves in a way that cannot be explained within the current framework, scientists ask whether the framework itself is missing something. In the early days of astronomy, planets moved in ways that did not match predictions. The solution was not to abandon physics, but to add unseen elements, new planets, new forces, new understandings. Neptune was discovered this way, inferred from its gravitational shadow long before it was directly observed. Flatland offers a quiet analogy for how inference works. If you were a three-dimensional observer watching the flat world, you would see the full picture. You would know that nothing supernatural was happening. A finger passed through a plane. A sphere rolled above it. A hand hovered briefly, casting shapes below. But the flat beings would have no access to that explanation unless they were willing to imagine a dimension beyond their experience. This is where the analogy becomes personal. You, too, live inside a set of dimensions that feel complete because they are sufficient for daily life. You can measure length, width, and height. You can track time. You can predict motion with remarkable accuracy. Your physics works extremely well. And yet, just as Flatland's physics breaks down when confronted with higher dimensional events, ours begins to strain at the edges of reality. At very small scales, particles behave as probabilities rather than objects. Very large scales, gravity behaves differently than expected. Forces that should unify remain stubbornly separate. These are not failures of observation, but hints that the underlying structure may be richer than it appears. Flatland also teaches something subtle about perception itself. The flat beings are not foolish for failing to imagine height. Their brains evolved to survive in two dimensions. Their senses detect what matters. Everything else is noise. To them, the idea of up would sound mystical, untestable, unnecessary. In the same way, higher spatial dimensions may feel unnecessary to us. We navigate the world just fine without them. Our bodies, tools, and instincts are tuned to three dimensions because that is what evolution required. Physics, however, is not bound by comfort. When mathematicians describe higher dimensions, they do so with the same precision used for lower ones. A four-dimensional cube, called a tesseract, is not a fantasy. It is a well-defined geometric object. Its properties can be calculated exactly. Its projections into three dimensions can be drawn, much like a cube can be drawn on a flat page. When you see a drawing of a cube on paper, you are already interpreting a higher dimensional object through a lower dimensional projection. Your brain reconstructs depth from perspective cues. You never see the cube directly on the page, you infer it. This is important. You already understand higher dimensions intuitively, you just don't label them that way. A shadow is a two-dimensional projection of a three-dimensional object. A photograph is another. A medical CT scan reconstructs three-dimensional structure from many two-dimensional slices. Each slice alone is incomplete. Together, they reveal the whole. Flatland's impossible slices are simply cross-sections. If a four-dimensional object passed through our space, we would experience something similar. Not the object itself, but a sequence of three-dimensional cross-sections appearing, changing, and vanishing. Matter might seem to materialize and dematerialize. Shapes might change topology in ways that seem forbidden. To us, it would feel uncanny. To the higher dimensional object, it would feel ordinary. This perspective gently reframes the question of reality. What we observe may not be everything that exists. It may be what intersects our dimensional slice of the universe. Even time fits this analogy. When you remember the past, you are not revisiting it. You are recalling a lower dimensional trace of a path already taken. The full space-time structure contains all those moments, but you experience them one slice at a time. Flatland also reveals something emotional about knowledge. The flat beings who accept only what they see live comfortably but narrowly. Those who begin to suspect higher dimensions experience confusion, resistance, even ridicule. Abbott's original story used this as a metaphor for human social limits, but the scientific parallel is striking. Progress often begins with ideas that feel impossible because they challenge the boundaries of perception. When Einstein proposed that time was not absolute, it sounded absurd. When quantum mechanics suggested particles could exist in superpositions, it felt impossible. And yet, nature did not care about intuition. Higher dimensions sit in that same quiet space between mathematics and observation. Flatland does not prove that higher dimensions exist. It does something more valuable. It shows that invisibility is not evidence of absence, that completeness is relative to perspective. As you rest now, imagine gently what it would be like to be a Flatland observer, confident, certain, at home in a universe that feels fully understood. And then imagine the quiet shock of realizing there might be more. Not chaos, not danger, just depth. Physics asks you to hold that possibility without anxiety, to let it be an open question rather than a threat. The universe does not become less stable because it is larger than expected. If anything, it becomes more elegant. And as we continue this slow journey forward, one question naturally follows. If a lower dimensional world can be embedded inside a higher one without its inhabitants noticing, then what would happen if our own three-dimensional space were embedded inside something larger still? And how would such a fourth spatial dimension reveal itself to us? Part 4. How a fourth spatial dimension would look. If a fourth spatial dimension existed, objects could move in ways that seem miraculous. A closed box could be entered without opening it. Knots could untie themselves without passing ends through loops. What feels like magic is simply geometry viewed from too few directions, the same way a shadow cannot explain the full shape of the object that casts it. To understand this calmly, it helps to begin with something familiar. Imagine a flat two-dimensional world again, one with no height at all. In that world, a simple closed curve, a circle drawn on the plane, divides space into inside and outside. There's no way to cross from one side to the other without breaking the boundary. To a flat being, the circle is an absolute barrier. Now, imagine lifting your finger above the plane. Without touching the circle, you lower the finger into the interior region. From the flat world's perspective, you have done the impossible. You entered a sealed space without crossing its boundary. No laws were broken. You simply used a direction they cannot access. This is the quiet heart of higher dimensional geometry. When physicists talk about the strange possibilities of a fourth spatial dimension, they are not invoking fantasy. They are extending the same logic that already applies between 2 and 3 dimensions. Every time you step over a line drawn on the ground, you are performing a higher dimensional escape from a lower dimensional constraint. A fourth spatial dimension would offer the same freedom relative to our three-dimensional world. In 3 dimensions, objects can be trapped by surfaces. A box encloses space. A sphere divides inside from outside. A knot ties a rope into a configuration that cannot be undone without cutting. These limitations feel absolute because all of our movements are confined to 3 directions. But geometry changes when an additional direction exists. In 4 spatial dimensions, a closed 3-dimensional surface, like a sphere or box, no longer fully encloses space. There is another direction available, perpendicular to all 3 you know. Through that direction, objects could bypass barriers effortlessly. To a 3-dimensional observer, the results would appear deeply unsettling. Objects might seem to vanish from one location and reappear in another without passing through the space in between. Knots could loosen themselves. Interlocked rings could separate without breaking. Yet from the higher dimensional perspective, everything would remain smooth and continuous. This idea becomes clearer when we think about projections. A shadow on the wall is a two-dimensional projection of a three-dimensional object. As the object moves, the shadow changes shape. It may stretch, split, merge, or disappear. The shadow itself obeys no conservation of shape because it is not the object. It is a slice of information. If a four-dimensional object passed through our three-dimensional space, what we would see is not the object itself, but a sequence of three-dimensional cross-sections. Shapes would appear, morph, and vanish in ways that defy ordinary intuition. Physicists sometimes illustrate this with a four-dimensional sphere called a hypersphere. If a hypersphere passed through our space, we would first see a single point appear. That point would grow into a small sphere, then expand, then shrink again, and finally vanish. At no moment would we see the full object. This is not science fiction. It is the direct four-dimensional analog of slicing a three-dimensional sphere with a plane. The discomfort arises not from inconsistency, but from incompleteness. Your intuition expects continuity within three dimensions. When that continuity is maintained outside your perceptual limits, the internal view looks discontinuous. The universe appears to break rules it never actually violates. This has profound implications for how we interpret strange phenomena. Physics is careful here. There is no evidence that everyday objects slip into higher dimensions. But the exercise reveals something deeper. Many impossibilities are only impossible within a limited frame of reference. The laws of geometry do not change. The number of accessible directions does. In four dimensions, even basic shapes behave differently. A cube becomes a tesseract, a four-dimensional hypercube. Just as a cube has square faces, a tesseract has cubic cells. It can be rotated in ways that have no three-dimensional equivalent. When projected into three dimensions, it appears to twist through itself, overlapping without intersecting. When you see diagrams of a rotating tesseract, the image looks paradoxical. Edges pass through faces, inside becomes outside, but nothing illegal is happening. The projection simply collapses information from four dimensions into three. You already accept this collapse in everyday life. A photograph flattens depth, a map flattens terrain. Perspective distorts scale. Your brain corrects these distortions automatically because it has learned how projections behave. With higher dimensions, the correction feels harder because there is no lived experience to anchor it. Another quiet consequence of a fourth spatial dimension is how it changes topology, the study of shape and connectivity. In three dimensions, knots matter. A knotted rope cannot be untied without cutting or passing one end through loops. In four dimensions, knots lose their permanence. The rope can be smoothly deformed through the extra direction until the knot disappears. This is not metaphorical. Mathematically, all knots can be untied in four dimensions without cutting. The constraint that defines a knot only exists because motion is restricted. Barriers, enclosures, and separations all rely on dimensional limits. This reframes how we think about confinement in physics. Many quantities feel conserved because they cannot escape. Charge, flux, fields. But if extra dimensions exist, they may offer hidden routes for interaction that are invisible to us. Physicists are cautious here, but curious. A fourth spatial dimension would not replace our world. It would contain it. Every point in space would have an additional direction attached, whether or not anything travels along it. You would not suddenly perceive it. Just as Flatland's inhabitants cannot see height, your senses would remain blind to the extra direction. The geometry would exist regardless. There is something gently humbling in this. Reality may be more permissive than experience suggests. What feels fixed and closed may be open in ways you cannot access. Even now, much of the universe behaves this way. Neutrinos pass through your body almost without interaction. Dark matter drifts through galaxies without touching light. These phenomena feel ghostly not because they are unreal, but because they occupy regimes of interaction your senses do not detect. Higher dimensions would be similar, not supernatural, simply unresponsive to the tools evolution provided. It is also important to say what a fourth spatial dimension would not be. It would not necessarily be a place where objects go to disappear. It would not be a parallel universe in the dramatic sense. It would be a geometric extension, governed by the same physical laws, integrated quietly into the structure of space. If such a dimension exists, it may be tightly constrained, curled, or energetically inaccessible. Or it may only reveal itself at scales far beyond everyday matter. Physics does not claim certainty here. It offers possibility, grounded in mathematics. And there's a quiet peace in that uncertainty. Science does not rush to fill gaps with stories. It leaves questions open until nature answers. As you listen now, you do not need to imagine moving through a fourth dimension. It is enough to notice how often impossibility dissolves when perspective changes, how often barriers are products of viewpoint rather than law. A shadow cannot tell you everything about the object that casts it. A slice cannot tell you everything about the whole, and a three-dimensional world may not tell the entire story of space. As we continue this calm exploration, another question gently emerges. If a fourth spatial dimension could exist without being visible, then why wouldn't we feel it at all? And what would keep such dimensions hidden from experience in the first place? Part 5. Why we don't feel higher. The dimensions. If extra dimensions exist, they are not large and open like the room around you. Physics suggests they may be compact, curled up at scales far smaller than atoms. You don't feel them for the same reason you don't feel the curvature of Earth beneath your feet. Some structures are too vast, others too small, to register through ordinary perception. To understand this, it helps to slow down and think about scale. Right now, the ground beneath you feels flat and stable. You can walk in a straight line without noticing any bend. And yet, the Earth is round, curving gently away beneath every step. The reason you don't feel that curvature is not because it isn't there, but because it changes too slowly over the distances your body can sense. Your experience is local. Earth's curvature is global. The same principle applies in the opposite direction. There are structures so small that your senses simply pass over them without notice. Individual air molecules move around you constantly, colliding with your skin, entering your lungs, bouncing off surfaces. You never feel each collision. Only their collective effect: pressure, temperature, wind. Perception is not a measure of existence. It is a filter shaped by usefulness. Physics suggests that if higher spatial dimensions exist, they may be hidden by scale in exactly this way. Not stretched out across cosmic distances, but tightly compacted, folded into the fabric of space itself at lengths far smaller than anything you can touch. To picture this calmly, imagine a very thin wire stretched across a room. From far away, it looks like a simple one-dimensional line. You can see its length, but not its thickness. Up close, however, the wire has structure. It has a circular cross-section. There is a direction you could move around it, even though that direction is invisible at larger scales. If you were a tiny creature living on the wire, that circular direction would matter. If you were large compared to the wire, it would not. In physics, this idea is formalized in the concept of compact dimensions. A compact dimension is one that loops back on itself, like a circle with a finite size. If that size is extremely small, motion along that dimension becomes difficult to detect. You could be moving through such a dimension constantly and never notice. This is not speculation without grounding. It is a direct extension of known geometry. A circle is a one-dimensional space, but it is finite. A cylinder combines an extended dimension with a compact one. From far away, the cylinder looks like a line. Only close inspection reveals the extra direction. Some theories propose that space itself may behave this way. In string theory, for example, extra dimensions are not spread out. They are compactified into tiny geometric shapes called Calabi-Yau manifolds. These shapes are incredibly small, on the order of the Planck length, far beyond the reach of current experiments. At that scale, the extra dimensions are not empty corridors. They are tightly folded patterns influencing the behavior of particles without offering room for large objects to move freely. This explains why you don't feel them. Your body is not small enough to respond to those directions. The energy required to probe them is far beyond anything present in everyday experience. There is another reason higher dimensions would feel invisible: uniformity. You only feel motion when there is a change. Acceleration, vibration, imbalance. Constant motion fades into stillness. This is why you don't feel Earth's rotation or its orbit around the sun. Everything around you is moving together. If higher dimensions are uniform and stable, they would offer no signal to your senses. No resistance, no gradient, no difference to detect. Even gravity, the weakest of the fundamental forces, reveals itself only through changes. A perfectly uniform gravitational field would be undetectable locally. This is one of the insights behind Einstein's equivalence principle. So the absence of sensation does not mean the absence of structure. There's also the question of confinement. Some theories suggest that while gravity can move through higher dimensions, other forces and particles are confined to our familiar three-dimensional space. In this view, your body, your atoms, and even light are restricted to a lower dimensional surface embedded within a higher dimensional space. This surface is sometimes called a brane, short for membrane. If this is true, then higher dimensions exist all around you, but you cannot move into them any more than ink on a page can lift itself off the paper. The restriction is not perceptual, but physical. This idea sounds dramatic, but it is mathematically precise. The equations of certain models naturally confine particles while allowing gravity to propagate more freely. The result is a universe that feels three-dimensional, even if it is not. This may also help explain why gravity is so weak compared to other forces. If gravity spreads into extra dimensions while electromagnetism does not, then its strength in our space would appear diluted. Again, this is not proven, but it is consistent. And consistency matters in physics. Another quiet reason we don't feel higher dimensions is time. Human experience unfolds over seconds, minutes, years. If higher dimensional effects occur at timescales far shorter or longer than this, they would blur into irrelevance. Quantum fluctuations happen constantly, but they average out. Cosmic expansion happens relentlessly, but too slowly to feel. Dimensions may influence reality subtly, shaping constants and interactions rather than producing dramatic sensations. Think of it this way. You do not feel the presence of every law of physics acting on you. You feel their outcomes: stability, solidity, continuity. Higher dimensions, if they exist, may already be contributing to those outcomes without ever announcing themselves. This reframes the idea of detection. We are not waiting to feel a new direction open beneath our feet. We are looking for small deviations, slight inconsistencies, gentle clues that suggest deeper structure. Physics experiments search for these clues in particle collisions, gravitational measurements, and cosmological observations. They look for missing energy, unexpected decay patterns, tiny anomalies in force laws. So far, nothing definitive has appeared, but the search continues, not with urgency, but with patience. There is something soothing about this approach. Science does not demand that reality conform to expectation. It listens, and it listens carefully, because nature often whispers. The fact that you don't feel higher dimensions may not be a flaw in your perception. It may be a feature of a universe that hides its complexity behind stability. Your world feels calm because it is governed by deep order. That order may arise from geometry richer than experience suggests. As you rest now, it may help to let go of the idea that feeling is the ultimate measure of reality. Much of what keeps you alive is invisible. Much of what shapes the universe operates silently. Higher dimensions, if they exist, would be no different. They would not intrude. They would not disrupt. They would simply be there, folded into the background of space, doing their quiet work. And as we move gently forward in this exploration, another question waits just beyond the horizon. If higher dimensions are compact and hidden, then how did physicists first begin to imagine them at all? And what problem were they trying to solve when these extra directions quietly entered the equations? Part 6. Kaluza, Klein, and the first hidden dimensions. In the early 20th century, physicists Theodore Kaluza and Oscar Klein proposed that electromagnetism could emerge from an extra-spatial dimension. Their idea was radical but precise. Forces we experience may be shadows of geometry in higher dimensional space. A hidden direction, tightly curled, could give rise to familiar physical laws without ever being directly observed. To appreciate how quietly revolutionary this idea was, it helps to remember the state of physics at the time. By the early 1900s, Einstein had already reshaped our understanding of gravity. His general theory of relativity showed that gravity was not a force in the traditional sense, but a manifestation of curved spacetime. Matter bent space and time, and that curvature guided motion. It was elegant, geometric, and deeply satisfying. But something remained unresolved. Electromagnetism, the force responsible for light, electricity, and magnetism, was described by a completely different set of equations. James Clerk Maxwell's equations worked perfectly, but they did not fit naturally into Einstein's geometric picture. Gravity was geometry. Electromagnetism was not. Physicists wondered whether this separation was fundamental or simply a limitation of perspective. In 1919, Theodore Kaluza proposed a daring solution. What if spacetime did not have 4 dimensions, but 5? What if, hidden alongside the 3 dimensions of space and 1 of time, there was an additional spatial direction? Kaluza noticed something remarkable. When Einstein's equations were written in 5 dimensions instead of 4, and then carefully simplified, the equations of electromagnetism appeared automatically. They did not need to be added by hand. They emerged naturally from the geometry. In this picture, gravity and electromagnetism were no longer separate forces. They were different aspects of the same higher dimensional structure. It was a stunning insight, but it raised an immediate and obvious question. If there is a 5th dimension, where is it? This is where Oscar Klein entered the story. In the 1920s, Klein proposed that the extra dimension was not extended like the familiar ones. Instead, it was compact, curled up into a tiny circle at every point in space, so small that it could not be detected directly. To imagine this, return to the idea of the thin wire. From far away, the wire looks one-dimensional. Up close, it has a circular direction wrapped around it. Klein suggested that space itself might be like that. At large scales, it looks 3-dimensional. At extremely small scales, it has additional structure. In Klein's model, the 5th dimension was wrapped into a circle with a radius on the order of the Planck length, far smaller than anything experiments could probe. Motion along that dimension would be quantized, allowed only in discrete amounts. These quantized motions would appear in 4 dimensions as electric charge. This was not metaphorical, it was mathematical. Electric charge, in this view, was not an intrinsic property added to particles. It was momentum in a hidden direction. What we experience as a force was reinterpreted as geometry. This idea was both beautiful and unsettling. It suggested that the universe might be simpler than it appears, unified at a deeper level, yet also far more complex in structure. The Kaluza-Klein model showed for the first time that extra dimensions were not a whimsical addition. They could solve real problems, they could unify forces, they could explain why certain quantities are quantized rather than continuous. And yet, the idea did not take hold immediately. There were difficulties. The model predicted additional particles that were not observed. It did not naturally include the nuclear forces. And without experimental evidence, physicists were cautious. Still, something important had happened. The door had been opened. For the first time, higher dimensions were not introduced as curiosities or thought experiments, but as necessary components of a serious physical theory. Geometry itself had become active. Space was no longer just where physics happened, it was what physics was. This shift in thinking had lasting consequences. Later, theories would return to this idea again and again. String theory, supergravity, and other modern frameworks all trace part of their lineage back to Kaluza and Klein. The core intuition remains the same. Forces may not be fundamental, they may be emergent, arising from the shape and structure of space in dimensions beyond perception. There is something quietly profound about this. It suggests that when you feel a force, when light bends, when magnets attract, you are witnessing geometry in action. Not geometry you can draw on paper, but geometry folded into the deepest layers of reality. Even if the specific Kaluza-Klein model does not describe our universe exactly, its lesson endures. Reality may be simpler at higher dimensions, and what feels complicated here may be the result of projecting that simplicity downward. Think again of Flatland. The inhabitants struggle to explain why shadows behave strangely. Their equations grow messy. They invent rules upon rules, but from above, everything is straightforward. A three-dimensional object moves smoothly through space. In the same way, higher dimensional geometry may offer clarity that is lost when reduced to fewer dimensions. There is also a calming humility in this realization. The limits of human understanding may not reflect limits of reality. They reflect limits of access. Kaluza and Klein did not propose their idea because they wanted reality to be stranger. They proposed it because it made the equations cleaner. This is often how progress happens in physics, not by chasing mystery, but by following simplicity. And simplicity, paradoxically, often leads to hidden depth. As the decades passed, physics would grow more intricate. Quantum mechanics would introduce uncertainty and probability. New forces would be discovered, particles would multiply. The dream of unification would seem to drift farther away. But the seed planted by Kaluza and Klein remained. The idea that extra dimensions could unify what appears separate, that geometry could replace force, that what we feel may be a projection of something we cannot see. Even now, experiments search quietly for signs of Kaluza-Klein physics, tiny deviations in particle behavior, unexpected resonances, subtle shifts in gravitational strength at small distances. So far, nature has remained reserved. But absence of evidence is not evidence of absence, especially when the scales involved are so extreme. What matters is that the idea changed how physicists think about dimensions. They were no longer optional. They were tools, and tools once discovered are rarely forgotten. As you rest and listen, it may be soothing to consider that the forces shaping your body and your world may arise from something elegantly simple, folded just beyond reach. That the universe, at its deepest level, may be written in geometry rather than machinery. Kaluza and Klein did not give us a final answer. They gave us a direction. And as we continue this gentle journey, another question naturally follows. If one hidden dimension could explain electromagnetism, then what might happen if there were many more? And how far would physics need to go before dimensions became not an exception, but a necessity? Part 7. String Theory's Many Dimensions. String theory suggests that the universe may require 10 or even 11 dimensions to remain mathematically consistent. These extra dimensions are not optional decorations. They are structural necessities in the equations. Within them, the vibrations of tiny strings determine particle properties, quietly translating higher dimensional motion into the matter you know. To understand why physics was led to such a startling conclusion, it helps to begin with a problem that has lingered for decades. Modern physics rests on two extraordinarily successful frameworks. Quantum mechanics describes the behavior of particles and forces at the smallest scales. General relativity describes gravity and the structure of spacetime at the largest. Each theory works beautifully in its own domain. Yet when physicists try to combine them, the equations break. At extreme energies such as those that existed near the beginning of the universe or inside black holes, quantum mechanics and gravity refuse to cooperate. Calculations produce infinities. Predictions lose meaning. Something essential is missing. String theory emerged as one possible answer to this tension. The core idea is simple, though its implications are vast. What if the fundamental building blocks of reality are not point-like particles, but tiny, vibrating strings? So small that even the most powerful experiments cannot resolve them. These strings can vibrate in different ways, and each vibration mode appears at larger scales as a different particle. An electron is not a thing unto itself. It is a pattern, a vibration. This shift from points to strings immediately softens many of the infinities that plague quantum gravity. Strings have size. They smear interactions over a tiny region, Instead of concentrating them at an infinitely small point, mathematics becomes more well-behaved. But as physicists developed the theory, something unexpected happened. The equations only worked if space had more dimensions than the 3 you know, not 4, not 5, 10, or in certain versions, 11. This was not a philosophical choice. When physicists tried to write the equations of string theory in fewer dimensions, inconsistencies appeared. Symmetries broke, anomalies arose, the mathematics simply refused to function. Only in higher dimensional space did the theory become self-consistent. This is a crucial point. String theory did not add dimensions to be extravagant. It was forced to accept them. In these models, spacetime consists of 9 spatial dimensions and 1 time dimension, or 10 spatial and 1 time dimension in more advanced formulations known as M-theory. The familiar 3 dimensions of space are extended and large. The others are compact, hidden at scales so small they have never been observed. Within these extra dimensions lies the key to particle physics. Strings vibrate not only in the dimensions you can see, but also in the dimensions you cannot. The shape and geometry of those hidden dimensions determine how strings are allowed to vibrate, and those allowed vibrations determine the masses, charges, and interaction strengths of particles. In this view, the properties of matter are not arbitrary, they are geometric. An electron has the mass it does because of how space is folded. A quark carries charge because of how strings move through unseen directions. Even the existence of different forces may arise from how dimensions are arranged. This idea is both unsettling and elegant. It suggests that the universe is not built from objects, but from patterns constrained by geometry. Matter becomes music, played on the instrument of space-time itself. The extra dimensions in string theory are often imagined as Calabi-Yau manifolds, complex shapes with intricate curvature. These shapes are not random. They must satisfy strict mathematical conditions to preserve stability and symmetry. There may be many possible shapes, each corresponding to a different version of physical laws. This leads to what physicists call the landscape of string theory, a vast space of possible universes, each with its own constants and properties. This idea is controversial. It challenges the hope that physics will one day predict every parameter uniquely. But it also offers a possible explanation for why the universe is the way it is. We exist in a universe whose hidden dimensions allow stars, chemistry, and life. Other configurations may exist only mathematically, silent and empty. Still, it is important to remain grounded. String theory is not experimentally confirmed. Its characteristic scales are far beyond what current technology can probe. The energies required to directly observe strings or extra dimensions are many orders of magnitude greater than those achievable in particle accelerators. And yet, string theory persists. It persists because it connects ideas that otherwise remain separate. It naturally includes gravity. It respects quantum mechanics. It unifies forces through geometry. It recovers known physics in appropriate limits. In science, such coherence matters deeply. There is also a philosophical calm in the idea that complexity emerges from simplicity. A single type of object, a string, gives rise to all particles and forces. Differences arise not from fundamental variety, but from allowed patterns of motion. You may notice how this echoes earlier ideas. Kaluza and Klein showed that electromagnetism could arise from a hidden dimension. String theory extends this logic dramatically. Not just one force, but all of them may be geometric shadows. Even time itself may be shaped by higher dimensional structure. In some formulations, space-time as you experience it is not fundamental. It emerges from deeper dynamics of strings and branes. Space and time become effective descriptions, useful at large scales, but not ultimate. This is a difficult idea to hold, but it fits the quiet pattern of scientific progress. Solid objects dissolve into atoms. Atoms dissolve into fields. Fields dissolve into geometry. Each layer feels abstract until it becomes familiar. There is also something deeply peaceful about the way string theory treats the universe. It does not imagine violent machinery behind reality. It imagines vibration, resonance, harmony. The universe hums. Even now, as you rest, your body is held together by forces that may trace their origin to tiny strings vibrating in unseen dimensions. You do not feel this vibration, you feel its average effects: solidity, warmth, continuity. The fact that you cannot sense the underlying structure does not make it less real. In this sense, string theory is an extension of a very old insight. Reality is not obligated to match intuition. It only needs to be consistent. And consistency, when followed carefully, can lead to surprising places. Physicists continue to explore string theory, not because it is fashionable, but because it refuses to fall apart. Every time it is pushed mathematically, it reveals deeper connections. Dualities show that seemingly different theories describe the same physics. Dimensions can trade roles. Space can emerge from entanglement. The universe, it seems, is flexible in ways experience never prepared you for. As you listen, there is no need to understand every detail. What matters is the pattern. Physics keeps returning to the same suggestion. What you see is not all that exists. What feels simple may be deeply structured. What feels fundamental may be emergent. String theory's many dimensions are one expression of that suggestion. And as we continue this gentle exploration, a new question begins to take shape. If these hidden dimensions determine the properties of matter itself, then what do they look like? And how does the specific shape of unseen space quietly decide the nature of everything you touch? Part 8. The shape of hidden space. Extra dimensions are not imagined as empty corridors, but as intricate geometric forms called Calabi-Yau manifolds. These shapes are folded, twisted, and balanced with extraordinary precision. Their geometry determines the masses and charges of particles, meaning the deep structure of reality may depend on shapes no human eye could ever see. To understand why shape matters so much, it helps to return again to something simple. Imagine a violin string. When it vibrates, the sound it produces depends on its length, its tension, and the way it is anchored at each end. Change the shape or boundary of the string, and the sound changes with it. The physics is the same, but the geometry determines the outcome. In string theory, the universe is filled not with violin strings, but with unimaginably tiny ones, vibrating at scales far beyond direct observation. And just like musical strings, the notes they can play depend on the space they vibrate within. That space, according to the theory, is not smooth and empty. It is shaped. Calabi-Yau manifolds are not objects floating somewhere else. They are patterns woven into every point of space. At each location you occupy, these hidden dimensions may exist as tightly folded structures, their geometry determining what kinds of vibrations are possible. This idea can feel abstract, but its logic is quiet and precise. In ordinary space, geometry already matters deeply. The shape of Earth determines gravity's pull. The curvature of spacetime determines how planets move. Even the shape of an atom determines how it bonds with others. Form and behavior are inseparable. Calabi-Yau geometry extends this principle into unseen dimensions. These manifolds are complex, meaning they require multiple coordinates to describe even locally. They are compact, finite in size, yet without boundaries. They are balanced, possessing mathematical properties that preserve symmetry and stability. One of the most important of these properties is something called Ricci flatness, a condition that allows the extra dimensions to exist without introducing unwanted forces or instabilities. This is not a decorative choice. Without it, the equations collapse. In other words, not just any shape will do. Only very specific geometries can support a universe like ours. This is where the idea becomes quietly profound. The mass of an electron, the strength of the electromagnetic force, the behavior of quarks, all may depend on how these hidden dimensions are folded. Change the shape slightly, and the physics changes with it. From this perspective, the laws of nature are not merely written into the universe, they are carved into its geometry. Physicists sometimes describe this as geometry determining physics, a phrase that echoes Einstein's view of gravity but reaches much deeper. Not only does geometry guide motion, it may define identity. This also explains why there could be many possible Calabi-Yau shapes. Mathematics allows a vast number of solutions, each corresponding to a different way of compactifying extra dimensions. Each solution yields a different set of physical constants. This collection of possibilities is often called the string landscape. The landscape is not a map of places, but of potential universes. Each point represents a different geometric configuration, a different way hidden space could be folded. Some configurations produce sterile universes with no stable matter. Others allow stars but no chemistry. A few may allow complexity, structure, and life. We find ourselves in one of those. This idea can feel unsettling, as though it threatens the uniqueness of reality. But it also offers a calm explanation for something that has puzzled physicists for decades: why the constants of nature seem finely tuned. Why is gravity so weak compared to other forces? Why do particles have the masses they do? Why does chemistry work at all? If these properties arise from geometry, then their values are not arbitrary. They are consequences, and consequences can be understood. Calabi-Yau manifolds are difficult to visualize because they exist in 6 or more dimensions, but mathematicians can study their properties through equations, symmetries, and projections. They can classify them, count their features, and calculate how strings would vibrate within them. Each allowed vibration corresponds to a particle. Each mode has a specific mass and charge. The shape of the manifold acts like a filter, permitting some patterns and forbidding others. In this way, matter becomes a shadow of geometry. It is worth pausing here to notice the pattern emerging across physics. Again and again, what once seemed fundamental becomes emergent. Forces become curvature, particles become vibrations, properties become geometry. This does not make the universe colder or more mechanical. It makes it quieter and more coherent. Hidden dimensions are not chaotic. They are exquisitely constrained, and yet their very abundance presents a challenge. With so many possible shapes, how do we know which one describes our universe? How do we test something so small and so abstract? At present, we do not know. Physicists search indirectly, looking for patterns in particle physics that hint at underlying geometry. They study symmetry breaking, coupling constants, and the spectrum of particles. They look for signs that spacetime has more structure than appears. So far, no definitive signature has emerged, but the absence of confirmation does not erase the insight. It refines it. Even if string theory in its current form turns out not to describe our universe, the lesson remains. Geometry is powerful. Space is active. The shape of what we cannot see may govern everything we can. There is also a quieter, more human way to hold this idea. You are made of matter whose properties may be decided by shapes folded at scales beyond imagination. Every breath, every sensation, every thought depends on particles behaving exactly as they do. Those behaviors may trace back to geometry hidden deep within spacetime. This does not diminish experience, it deepens it. It means that the ordinary world is not superficial. It is the visible surface of something extraordinarily intricate, and perhaps that is why the universe feels so stable. The hidden dimensions, if they exist, are not changing wildly. They are locked into precise configurations, holding the fabric of reality steady across billions of years. Change happens slowly, if at all. As you rest now, imagine that beneath the space you know, there is a delicate architecture, folded and balanced, doing its work silently. Not watching, not judging, simply shaping. The idea does not ask you to believe, it asks you to consider. What if the universe is not just large, but detailed? Not just expansive, but finely structured? What if reality's deepest truths are written not in explosions, but in quiet geometry? And as we continue this gentle exploration, another question begins to unfold. If the shape of hidden space determines the properties of matter, then how might those extra dimensions influence the forces we feel most strongly? And could one of them, gravity itself, be reaching beyond the space we know? Part 9. Gravity's strange weakness. Gravity is far weaker than the other fundamental forces, and higher dimensions may explain why. Some theories propose that gravity leaks into extra dimensions, spreading itself thin while other forces remain confined to the dimensions we inhabit. What feels like weakness may be dispersion across unseen directions. To appreciate how unusual gravity truly is, it helps to pause with a simple comparison. Hold a small magnet near a paperclip. With almost no effort, the paperclip lifts against the entire gravitational pull of the Earth. Every atom in the planet is pulling downward, and yet a tiny magnetic force overcomes it instantly. This is not a coincidence, it is a clue. Gravity is astonishingly weak. Compared to electromagnetism, gravity is weaker by a factor of about 1036. That number is so large it is difficult to hold intuitively. It means that gravity must act collectively across enormous amounts of mass to become noticeable at all. And yet, despite this weakness, gravity shapes galaxies, stars, and the large-scale structure of the universe. This imbalance has puzzled physicists for generations. Why should one force be so feeble while others are so strong? Why does gravity seem almost reluctant to act, whispering while other forces speak loudly? One possible answer lies not in what gravity is, but in where it can go. In the late 1990s, physicists began to explore models in which our familiar universe is embedded within a higher dimensional space. In these models, all the particles and forces you know, electromagnetism, the strong force, the weak force, are confined to a lower dimensional surface, a brane. But gravity is different. Gravity, they proposed, may not be confined at all. It may move freely through the extra dimensions. If this is true, then gravity would not be weak in an absolute sense. It would be diluted. Like light spreading out as it leaves a flashlight, gravity would fan out into dimensions we cannot access, leaving only a small fraction of its strength behind in our three-dimensional space. What you feel would be the remainder. This idea draws on a simple geometric principle. The strength of a force depends on how it spreads through space. In 3 dimensions, gravitational strength falls off with the square of the distance, double the distance, and the force becomes 4 times weaker. But if space has more dimensions, the force spreads more rapidly. It thins out faster. What feels weak locally may be the echo of something stronger acting across a larger arena. From this perspective, gravity's weakness is not a flaw. It is a signature. This possibility was explored in models known as large extra dimensions, most notably by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Gia Dvali. Their work suggested that extra dimensions might be larger than previously imagined, perhaps as large as a fraction of a millimeter, while remaining hidden to all forces except gravity. In such a universe, gravity appears weak because most of it escapes into the extra dimensions. Experiments have tested this idea carefully. Physicists have measured gravity at extremely small distances, searching for deviations from the inverse square law. So far, gravity behaves exactly as expected down to very small scales. If extra dimensions exist, they are either smaller or more subtle than these models first suggested. Still, the idea reshaped how physicists think. It reframed gravity not as an outlier, but as a messenger. A force that hints at dimensions beyond perception precisely because it refuses to stay confined. There is also something quietly poetic about this. Gravity is the force you feel most intimately. It keeps your feet on the ground. It gives weight to your body. It anchors oceans and atmosphere. And yet, it may be the one force most connected to the unseen, the one that reaches beyond. In Einstein's theory of general relativity, gravity is not a force at all. It is geometry. Mass curves spacetime, and objects follow the resulting paths. If spacetime has more dimensions than we perceive, then gravity would naturally reflect that structure. It would sense curvature not only in visible directions, but in hidden ones as well. This makes gravity uniquely suited to probe higher dimensions. While other forces may be trapped on a brane, gravity's geometric nature allows it to roam. If this is correct, then black holes become especially interesting. A black hole is a region where gravity dominates completely. Near its event horizon, gravity is so strong that even light cannot escape. If extra dimensions exist, black holes might interact with them directly. Their structure, evaporation, and formation could carry subtle imprints of higher dimensional space. Physicists have explored how black holes might behave differently in higher dimensions. In some models, microscopic black holes could form in high-energy particle collisions, briefly revealing the presence of extra dimensions before evaporating. So far, no such events have been observed, but the search continues, patiently. There's also a cosmological side to this story. Gravity governs the expansion of the universe. It shapes the growth of galaxies and the motion of clusters. If gravity can leak into extra dimensions, it could influence cosmic evolution in subtle ways. It might affect how fast the universe expands or how structures form over time. Some theories suggest that dark energy, the mysterious force accelerating cosmic expansion, could be related to higher dimensional gravity. Not as a substance, but as a geometric effect. Again, this remains speculative, but it shows how deeply gravity is entwined with questions of dimensionality. What is striking is how calm these ideas are. They do not require dramatic portals or violent transitions. They do not imagine space tearing open. They simply extend geometry gently, asking whether the structure beneath reality might be broader than experience suggests. If gravity does leak into extra dimensions, you would not feel it happening. You would only feel the result, a force that seems inexplicably weak, yet universally influential. There's a kind of balance here. The force that reaches the farthest acts the most softly. Gravity touches everything everywhere, but never overwhelms locally. It allows complexity to form. It lets stars burn slowly. It gives life time. If gravity were as strong as electromagnetism, the universe would collapse into dense clumps almost instantly. There would be no long-lived stars, no stable planets, no gentle surfaces to stand on. Gravity's weakness is not just curious, it is essential. Higher dimensions, if they exist, may be part of the reason the universe is hospitable. By allowing gravity to spread out, they keep it from dominating too quickly. This is not a claim of design, it is an observation of consequence. Physics often finds that what seems finely tuned emerges naturally from deeper structure. Weakness may be the shadow of abundance, gentleness may arise from freedom. As you rest now, it may be comforting to think of gravity not as fragile, but as generous, willing to share itself across dimensions, willing to shape without crushing. The ground beneath you holds because gravity is just strong enough. The stars above you shine because gravity is just gentle enough, and perhaps both facts trace back to unseen directions, quietly absorbing its reach. As we continue this slow exploration, another question begins to form. If gravity alone can move through higher dimensions, then what does that say about the nature of space itself? And could our entire universe be something like a surface floating within a much larger multidimensional reality? Part 10. Branes and Layered Universes. In higher dimensional models, our entire universe may exist on a membrane, or brane, floating within a larger multidimensional space. Particles and light remain bound to this surface, while gravity alone can wander between layers. If true, the cosmos is not empty space, but a quiet stack of worlds, passing close without touching. To approach this idea gently, imagine a single sheet of paper drifting through a vast, silent room. To a creature living on the sheet, the paper is the entire universe. There is forward and backward, left and right. There is no awareness of the room around it, even though the sheet is fully immersed within it. The room exists, but the creature has no way to step off the page. This is the essence of a brane world. In modern theoretical physics, a brane is a lower dimensional surface embedded within a higher dimensional space, sometimes called the bulk. Our familiar universe, with its 3 dimensions of space and 1 of time, may be such a surface. Everything you see, touch, and interact with could be confined to this thin layer, drifting quietly through a much larger reality. The idea may sound dramatic, but it arises naturally from string theory and related frameworks. In these theories, strings can have endpoints. Those endpoints are not free to roam everywhere. They are often anchored to branes. As a result, the particles formed by vibrating strings are restricted to move along the brane as well. Light, electrons, quarks, atoms, planets, all remain bound. Gravity, however, is different. Because gravity arises from the geometry of space-time itself, it does not require string endpoints in the same way. Gravitational interactions are carried by closed strings which have no endpoints and are free to move through the bulk. This gives gravity access to dimensions that other forces cannot enter. This distinction is crucial. It explains in a single geometric picture why gravity behaves differently from every other force, why it is weaker, why it reaches farther, why it refuses confinement. In a brane world scenario, gravity is not escaping our universe because it is weak. It is weak because it escapes. This transforms the way we think about space. Space is no longer just the region between objects. It becomes layered, structured, multidimensional. Our universe becomes one surface among potentially many, each separated by distances that may be tiny or vast in the higher dimensional bulk. These layers would not collide or interact easily. They would pass close without touching, like pages in a book. To us, the universe would still appear empty and continuous. The presence of other branes would be invisible unless gravity or other rare interactions bridge the gap. This raises a remarkable possibility. There could be other universes incredibly close to ours, separated not by distance in the usual sense, but by position in an unseen dimension, a separation of a fraction of a millimeter or less, and yet completely unreachable. This is not the multiverse of branching timelines or speculative fiction. It is a geometric multiverse, grounded in equations, quiet, and restrained. Physicists take care here. These ideas are models, not confirmed descriptions. But they are consistent, they obey known laws, they extend existing theories without breaking them, and consistency is a powerful guide. Brane models also offer new ways to think about cosmic events. The Big Bang, for example, could be interpreted not as the beginning of all space, but as a collision or interaction between branes. Energy released in such an encounter could ignite a hot, dense universe on a brane, while the bulk itself remains calm and timeless. This idea reframes creation not as an explosion into nothingness, but as a localized event within a larger structure. Again, this is not proven, but it illustrates how higher dimensions allow new interpretations without requiring supernatural assumptions. There is something quietly humbling in this picture. Your universe may not be the entirety of existence. It may be one surface among many, each complete in itself, each governed by its own physics, each unaware of the others except through faint gravitational whispers. And yet, this does not make your experience smaller. It makes it more specific. Just as Earth is one planet among billions and still meaningful, a brane universe can be one among many and still complete. There's also a calming stillness to the idea of layered universes, not colliding chaotically, not competing, but coexisting in silence, each following its own history, each unfolding gently over time. If such layers exist, they do not intrude. They do not announce themselves. They simply are. Brane world models also help physicists think about the hierarchy problem, the question of why gravity is so much weaker than other forces. If the gravitational field spreads into extra dimensions, then the strength we observe is only a shadow of its true magnitude in the bulk. From this perspective, the universe you inhabit is not fragile. It is buffered, protected by geometry. There are also experimental implications. If extra dimensions are large enough, gravity might deviate slightly from known behavior at very small distances. Physicists have tested this carefully, measuring gravitational attraction at millimeter and sub-millimeter scales. So far, gravity behaves as expected, but the search continues. Particle accelerators also look for signs of energy disappearing into extra dimensions. If collisions produce gravitons that escape the brane, detectors would record missing energy. Again, no definitive signal has appeared, but absence does not mean failure. It means refinement. Theories evolve, models sharpen, predictions become more precise. There's another subtle implication of brane worlds that is often overlooked. If particles are confined to a brane, then the dimensionality of space is not just a fact of nature. It is a condition, a constraint. something that could, in principle, be different elsewhere. This suggests that the number of large dimensions you experience is not inevitable. It may be contingent, the result of how space settled, how branes formed, how geometry stabilized. 3 dimensions may not be special because of necessity, but because of stability. This idea echoes throughout physics. Stable atoms have certain structures, stable orbits have certain shapes, stable universes may have certain dimensionalities. In fact, studies suggest that long-lived complex systems like stars and atoms may only exist in a small range of dimensional configurations. Too many dimensions, and gravity weakens too quickly. Too few, and stable orbits fail. If that is true, then the layered universe picture becomes not extravagant, but economical. Many possibilities exist, only some persist. As you rest now, it may be soothing to imagine your universe as a quiet surface, floating gently within a deeper expanse, not isolated, not exposed, but held within a larger geometry that does not disturb it. The stars above you, the ground beneath you, the body you inhabit, all remain exactly as they are. Nothing changes because of this idea, only the context deepens. And as we continue this calm exploration, another question begins to surface. If our universe is one brane among many, drifting in a higher dimensional space, then could the unseen matter shaping galaxies be something that exists just beyond our layer? And might dark matter itself be evidence of neighboring worlds we cannot touch? Part 11. Could higher dimensions explain dark matter? Dark matter reveals itself only through gravity, never through light. Some physicists wonder whether its effects arise from matter existing in nearby dimensions, gravitationally close but otherwise unreachable. The unseen mass-shaping galaxies may not be missing at all, but simply elsewhere. To begin gently, consider what dark matter is not. It is not darkness in the ordinary sense. It does not absorb light, emit light, or reflect light. Telescopes do not see it directly. No photograph has ever captured it, and yet its presence is unmistakable. Galaxies rotate too quickly. Clusters of galaxies hold together too tightly. Light from distant stars bends more than visible matter alone can explain. Everywhere astronomers look, gravity points to something unseen. This invisible influence is called dark matter, and it outweighs ordinary matter by roughly 5 to 1. Every star, planet, and atom you know appears to be a minority component of the universe. For decades, the leading explanation has been that dark matter is made of unknown particles, massive, slow-moving, weakly interacting particles that drift through space, shaping gravity, while ignoring light. Experiments deep underground and in space continue to search for them. So far, none have been conclusively detected. This has led physicists to ask quieter questions. What if dark matter is not missing at all? What if it is simply not here in the way we expect? Higher dimensional theories offer a subtle possibility. If gravity can move between dimensions, as some models suggest, then matter existing on nearby branes or within extra dimensions could exert gravitational influence on our universe without interacting electromagnetically. To us, that influence would look exactly like dark matter. In this view, dark matter is not invisible because it is made of strange particles. It is invisible because it does not live entirely in our dimensional layer. It lives next door. Imagine again the layered universe from the previous part. Multiple branes floating close together in a higher dimensional space. Matter on one brane cannot interact with matter on another through light or touch. But gravity, free to roam through the bulk, connects them. From your perspective, matter on a neighboring brane would be undetectable except through its gravitational pull. You would never see it. You would never feel it directly. But its mass would shape the motion of stars and galaxies in your own universe. It would look like dark matter. This idea is appealing not because it is dramatic, but because it is conservative. It does not invent new forces or abandon known physics. It uses gravity exactly as we understand it, extending only the geometry in which gravity operates. There is also something quietly elegant about this explanation. Dark matter behaves as if it is cold, collisionless, and smoothly distributed. These properties would naturally arise if it consisted of ordinary matter confined to another dimensional surface. No exotic behavior is required. Physicists have explored models where dark matter arises from bulk fields, shadow branes, or mirror worlds. In some versions, there could be an entire parallel copy of particle physics existing nearby, sharing gravity but nothing else. In others, matter might partially extend into extra dimensions, appearing diffuse and ghost-like from our point of view. Each of these models makes subtle predictions about how dark matter should behave, how it clusters, how it affects cosmic structure, how it responds to gravitational waves. So far, observations remain consistent with many possibilities. Dark matter does not form stars. It does not clump as tightly as ordinary matter. It creates broad halos around galaxies rather than sharp disks. These features are often cited as evidence for particle dark matter, but they could also arise from geometric separation. If matter exists in a nearby dimension, its distribution need not mirror ours exactly. It would follow its own dynamics, shaped by its own interactions, while still contributing to the overall gravitational landscape. There is a particularly striking piece of evidence that keeps this question open: gravitational lensing. When light from distant galaxies passes near massive clusters, it bends. By measuring this bending, astronomers can map where mass lies, regardless of whether it emits light. These maps consistently show large amounts of mass offset from visible matter. In some cases, such as the famous bullet cluster, dark matter appears to pass through collisions unaffected, separating cleanly from ordinary matter. This behavior fits well with the idea of collisionless particles, but it also fits with matter that does not reside in our space at all. Matter in another dimension would not collide with ours, even during violent cosmic events. It would glide through, interacting only gravitationally. Again, this does not prove the idea, but it keeps it alive. There is also a deeper philosophical calm in considering that dark matter may not be exotic. It may be familiar matter, obeying familiar laws, simply located somewhere we cannot reach. This reframes the mystery. Instead of asking, what strange substance fills the universe, we ask, how large is the universe really? Higher dimensions offer space for mass without cluttering our own. They offer a way for gravity to sense more than we can see, and gravity, once again, becomes the messenger. There are challenges to this idea, of course. Any higher dimensional explanation must reproduce the precise way dark matter behaves across cosmic time. It must fit observations of the early universe, the cosmic microwave background, and the formation of large-scale structure. Some models do this better than others. None have yet emerged as definitive. But the exercise itself is valuable. It shows how deeply geometry influences interpretation, how the same observation can point to particles, dimensions, or something else entirely, depending on context. Dark matter teaches humility. We have mapped galaxies billions of light years away. We have measured the age of the universe to remarkable precision. And yet, most of what gives the universe its mass remains unknown. Perhaps that is not a failure of detection, but a hint about structure. Perhaps the universe is not just full, but layered. There is also something comforting in the thought that dark matter is not hostile or dangerous. It does not tear galaxies apart. It holds them together. It stabilizes cosmic structures, allowing stars to form and persist. Whatever dark matter is, it appears to be patient. If it exists in other dimensions, then those dimensions are not chaotic realms. They are calm environments, evolving slowly, influencing ours gently. The universe, seen this way, is not a battlefield of forces, but a quiet arrangement of interacting layers. As you rest now, you may imagine galaxies turning slowly, guided by gravity that feels more than it sees. You may imagine unseen mass-shaping motion without ever revealing itself to light. Dark matter does not rush. It does not announce itself. It simply exists, exerting its influence over billions of years. And perhaps that is the deepest lesson it offers. Reality does not require visibility to matter. Influence does not require contact. Presence does not require perception. As we continue this calm exploration, another question naturally arises. If dark matter might reside beyond our dimensions, shaping the universe from just out of reach, then what does that imply about the earliest moments of creation? And could higher dimensions have played a role in how the universe itself began? Part 12. Higher dimensions and the beginning of the universe. The early universe was hotter, denser, and more symmetrical. In those conditions, extra dimensions may have been large and active, only shrinking as the universe cooled. The space you inhabit now may be a quiet remnant of a far richer geometric past. To approach this idea gently, it helps to imagine the universe not as something that suddenly appeared fully formed, but as something that unfolded. In its earliest moments, the universe was not structured the way it is now. There were no stars, no atoms, no galaxies. There may not even have been distinct forces. Everything was compressed into a state of extraordinary density and energy, where differences we now take for granted had not yet emerged. Physicists often describe the early universe as highly symmetrical. This does not mean orderly in a visual sense, but uniform in its laws. Forces that are separate today, gravity, electromagnetism, the nuclear forces, may once have been unified, expressions of a single underlying interaction. Space itself may have been more flexible, more evenly balanced between its possible directions. In such a state, higher dimensions would not necessarily have been hidden. Some theories suggest that in the first fractions of a second after the Big Bang, all dimensions of space may have been comparable in size, not curled tightly, not compacted, but open and active. Space may have had many directions in which to expand, many degrees of freedom unfolding at once. Then, as the universe cooled, something changed. As energy dropped and symmetry broke, certain dimensions expanded rapidly, while others stabilized and contracted. 3 spatial dimensions grew large and extended, forming the space you move through now. The remaining dimensions settled into compact forms, folded into themselves, and locked into place. This process is sometimes called dimensional compactification. It is not imagined as a violent collapse, but as a gradual settling, like a liquid cooling into a crystal. Certain configurations are stable, others are not. Over time, the universe naturally selects the shapes that can persist. In this view, the number of large dimensions you experience is not arbitrary. It is the result of a cosmic phase transition. This idea mirrors patterns seen elsewhere in physics. When water freezes, countless molecular motions give way to a specific lattice structure. When a magnet cools, random spins align in a particular direction. Symmetry breaks, and structure emerges. The early universe may have undergone similar transitions, but on a geometric level. If higher dimensions were once extended, they may have influenced the universe in ways that are still visible today. Tiny imprints in the cosmic microwave background, subtle correlations in large-scale structure, or the specific values of physical constants may carry traces of that early geometry. These traces would be faint. Billions of years of expansion would dilute them, but they would not vanish entirely. In some cosmological models, inflation, the rapid expansion thought to have occurred shortly after the Big Bang, is tied to the behavior of extra dimensions. The energy stored in their geometry could drive expansion, then release it as the universe settles into a lower energy configuration. In this picture, the dramatic growth of space is not an isolated event. It is connected to the reshaping of dimensions themselves. This idea also offers a new way to think about beginnings. The Big Bang is often imagined as the creation of everything from nothing. But in higher dimensional cosmology, it may represent a transition rather than an origin, a rearrangement of geometry, a moment when dimensions differentiated and space chose a particular form. Before that moment, reality may have existed in a state that does not resemble space and time as you know them. This does not remove mystery. It deepens it, but it replaces abrupt creation with gradual emergence, a theme that appears repeatedly in physics. Complex behavior arises not from sudden invention, but from simple rules unfolding under changing conditions. There is also a quiet humility in this view. The universe you inhabit may not be the first configuration space ever took. It may not be the only one possible. It may simply be the one that stabilized, and stability matters. 3 large spatial dimensions allow for long-lived orbits. They allow stars to burn steadily. They allow chemistry to form complex molecules. Other dimensional configurations may be mathematically possible but physically unstable, collapsing too quickly or dispersing too rapidly to support structure. In that sense, the universe you experience is not guaranteed. It is selected, not by intention, but by physics. Higher dimensions in the early universe would also help explain why the laws of nature appear finely balanced. If many configurations were possible, but only a few were stable, then the values we observe may be the survivors of a vast process of elimination. This does not require invoking purpose. It requires acknowledging selection. There is also an emotional calm in realizing that the universe did not rush to become what it is. It cooled, it settled, it differentiated slowly. Time itself emerged alongside structure, giving events a sequence and direction. The past you cannot remember may have been richer in symmetry than the present. The simplicity you feel now may be the result of a long process of refinement. Even today, the universe continues to evolve. Space expands, galaxies drift apart, structures slowly thin out. The hidden dimensions, if they exist, may remain stable, or they may evolve on timescales far beyond human awareness. Physics does not yet know. What it does know is that the early universe was different in kind, not just in degree. Temperatures were higher, densities were greater, forces behaved differently. Geometry itself may have been fluid. Higher dimensions fit naturally into that picture. They do not intrude into the calm of the present because the conditions that made them active no longer exist. They are relics, folded away as the universe cooled, leaving behind a quieter, more orderly space. In this sense, your universe is like the surface of a cooled object, solid, structured, stable. Beneath it lies a history of motion and transformation. As you rest now, it may be soothing to imagine the universe as something that has learned how to be still. Not static, but balanced. Not frozen, but settled into a form that allows complexity to persist. The space around you feels simple because it is the outcome of countless prior possibilities. And this leads gently to another question. If higher dimensions were once active and then compacted, shaping the birth of space and time themselves, then what role might they still play in the nature of time? And could time itself be an emergent feature of deeper dimensions rather than a fundamental one? That is where our quiet journey continues next. Part 13. What higher dimensions mean for time. In some models, time itself may emerge from motion through higher dimensions. What you experience as the steady flow of moments could be a projection of deeper dynamics unfolding beyond the familiar four. Time may not be fundamental, but a consequence of hidden structure. To approach this idea gently, it helps to notice how strange time already is, even before higher dimensions enter the picture. You never encounter time directly. You do not touch it or see it. You sense it only through change, a breath beginning and ending, light shifting across a room, a thought rising and fading. When nothing changes, time becomes almost invisible. Physics reflects this subtlety. In the equations that describe the universe, time often behaves differently from space, yet it is inseparable from it. Events are not placed in time alone, but in spacetime, and spacetime itself may not be the deepest layer of reality. Some modern theories suggest that time, like temperature or pressure, is an emergent quantity. It is real and measurable, but not fundamental. It arises from more basic processes, just as warmth arises from the collective motion of atoms. Higher dimensions offer one possible source of that emergence. In certain models, what we call time is not an independent direction at all. Instead, it is a measure of how systems evolve as they move through higher dimensional space. Change in this view comes from geometry, not from an external ticking clock. To picture this, imagine a long, winding path through a landscape. If you walk along the path, your position changes continuously. You could describe your progress in terms of distance traveled, but that distance is not something separate from the path itself. It is an accounting of motion. Now imagine that space-time itself is such a path, embedded within a higher dimensional structure. Time would then be a way of tracking movement through that structure, rather than a standalone dimension. This idea appears in several areas of theoretical physics. In certain approaches to quantum gravity, time does not appear explicitly in the fundamental equations. Instead, it emerges when the universe is described at larger scales, where correlations and sequences become meaningful. At the deepest level, there may be no universal now, only relationships. Higher dimensions provide room for these relationships to unfold. In string theory and related frameworks, space-time itself can emerge from the interactions of more fundamental objects. In some cases, the extra dimensions are not merely spatial, but dynamic. Motion through them can generate effects that look like temporal evolution when projected into lower dimensions. From this perspective, time is a shadow, not an illusion, but a projection. Just as a shadow moves when the object casting it moves, moments pass because deeper structures evolve. You experience the shadow because you inhabit the projection. This helps explain why time feels directional, why there is a past and a future, but no easy way to reverse them. If time emerges from underlying processes that have a preferred direction, such as increasing entropy or expanding geometry, then the arrow of time is inherited, not imposed. Higher dimensional motion does not need to be symmetric to produce asymmetric experience. There is also a calming implication here. If time is emergent, then it is not something you are racing against. It is something arising with you. Your experience of duration is tied to physical processes unfolding in harmony, not to an external clock counting down. In everyday life, this is already true. Time feels slow when little changes. It feels fast when change is dense. Physics formalizes this intuition by linking time to state change. Higher dimensions simply extend the idea further back. There are also models in which what we perceive as time corresponds to the size or shape of extra dimensions changing. As hidden dimensions evolve, their dynamics influence the effective laws of physics in our space. Observers confined to the lower dimensional world interpret this evolution as the passage of time. In such a universe, time is not a backdrop. It is a record. This also reframes the question of beginnings and endings. If time emerges from deeper structure, then asking what came before time may be like asking what lies north of the North Pole. The question assumes a framework that does not apply. Higher dimensions allow for reality to exist without time as we know it, then give rise to time when conditions are right. This idea appears in some approaches to cosmology, where the early universe is described by a timeless quantum state. Time emerges only after certain symmetries break and classical behavior takes over. The universe does not begin in time. Time begins in the universe. There is something deeply quiet about this view. It removes urgency. It replaces ticking clocks with unfolding patterns. It suggests that the present moment is not a fleeting instant, but a stable slice of a larger structure. In space-time diagrams, your life is not a point racing forward. It is a line extending calmly through the geometry of the universe. Past moments do not vanish. Future moments are not rushing toward you. They exist as parts of the same structure, connected by physical law. Higher dimensions deepen this picture by suggesting that even space-time itself may be a slice. You experience reality one cross-section at a time. This does not mean the future is fixed in a simple sense. Physical laws still allow for uncertainty, probability, and choice. Quantum mechanics introduces genuine unpredictability. Emergent time does not eliminate freedom. It contextualizes it. Your decisions shape which paths are realized within the structure, even if the structure itself is broader than experience. There is also an emotional comfort in realizing that time is not something separate from you. It is not an external force pushing you forward. It is a measure of change within a universe you are part of. You are not carried by time, you participate in it. Higher dimensions, if they underlie time, make this participation deeper. They suggest that what feels like flow is really relation. What feels like loss is really separation in geometry. What feels like anticipation is really orientation within structure. Physics does not claim to have settled these ideas. They remain areas of active research and debate, but their presence signals something important. Our most basic intuitions about reality, space, time, sequence, may be approximations, useful, reliable, but not ultimate. And this is not unsettling. It is freeing. It means that the universe is not constrained to match how it feels at human scales. It means that calm, order, and meaning can exist even if the underlying picture is richer than perception suggests. As you rest now, you may notice your breath rising and falling. That rhythm gives you a sense of time passing. But the breath itself is a process, a sequence of changes. Time is the name you give to that sequence. Higher dimensions invite you to imagine that all sequences arise this way, from deeper motion, from hidden structure. Moments do not fall away into nothing. They take their place within a larger pattern. And as we continue this gentle exploration, another question begins to form. If time itself may emerge from deeper dimensions, then how could we ever test such ideas? And is it possible, even in principle, to detect the presence of higher dimensions through experiment rather than imagination? That question carries us softly into the next part of our journey. Part 14. Can we ever detect higher dimensions? Physicists search for higher dimensions indirectly through subtle deviations in gravity, particle collisions, and cosmological measurements. The evidence, if it exists, will not arrive dramatically. It will appear as a quiet mismatch between expectation and observation, a whisper rather than a signal. To begin, it helps to release the image of discovery as a sudden revelation. No hidden door opening, no fabric of space tearing apart. If higher dimensions exist, they are likely subtle, restrained, and patient. Their presence would not announce itself loudly. It would reveal itself only through careful listening. Physics has learned this lesson before. Atoms were not discovered by seeing them directly, but by noticing patterns in chemical reactions. Neutrinos were inferred long before they were detected, introduced to preserve balance in equations. Black holes were once purely mathematical objects, accepted decades before evidence accumulated in the sky. Higher dimensions would follow this same path. They would be known by their effects, not by their appearance. One of the most direct ways physicists search for extra dimensions is through gravity. Because gravity is so weak, and because it may be free to move through higher dimensions, it is considered the most sensitive probe of hidden space. If extra dimensions exist, gravity might behave slightly differently at very small distances. The familiar inverse square law could begin to fail, not dramatically, but gently. At distances comparable to the size of the extra dimensions, gravity might spread into additional directions, weakening faster than expected. To test this, physicists have performed exquisitely delicate experiments, measuring gravitational attraction at millimeter and sub-millimeter scales. These experiments are quiet and patient, isolating tiny forces from vibration, temperature, and noise. So far, gravity has behaved exactly as predicted by three-dimensional space. This does not close the door. It narrows it. If extra dimensions exist, they must be smaller, more subtle, or structured in ways that evade these tests. Physics advances not by certainty, but by refinement. Another avenue of detection lies in particle physics. At extremely high energies, such as those produced in particle accelerators, extra dimensions might briefly reveal themselves. Collisions could produce particles that escape into higher dimensions, carrying away energy. To detectors, this would appear as missing energy, a discrepancy between what went in and what came out. Experiments at the Large Hadron Collider have searched carefully for such signatures. They look for patterns that cannot be explained by known particles alone. Again, nothing definitive has appeared. But here, too, absence is not failure. It is information. The energies accessible to current accelerators may simply be too low. If extra dimensions are compact at scales far smaller than a proton, the energy required to probe them would be enormous, far beyond present capabilities. There's also a cosmic laboratory that physics uses constantly. the universe itself. Cosmology offers another window into higher dimensions, one that spans billions of years and unimaginable distances. The cosmic microwave background, the faint afterglow of the Big Bang, carries subtle information about the early universe. Tiny fluctuations in its temperature encode details about how space expanded, how matter clustered, and how forces behaved when the universe was young. If higher dimensions played a role in the early universe, they may have left faint imprints in this radiation. Slight deviations from perfect uniformity, unexpected correlations, anomalies that resist simpler explanations. Cosmologists study these patterns with extraordinary precision. Satellites like Planck have mapped the microwave background down to minute details. So far, the data align remarkably well with standard cosmological models, and yet there are hints. Small tensions, slight mismatches between different measurements of cosmic expansion. These may resolve with better data, or they may point to deeper structure. Physics remains patient. Gravitational waves offer another possibility. These ripples in spacetime, produced by colliding black holes and neutron stars, travel vast distances before reaching Earth. If spacetime has extra dimensions, gravitational waves might leak into them, altering their strength or shape as they propagate. Detectors like LIGO and Virgo are sensitive enough to measure subtle features of these waves. As more events are observed, physicists can compare their behavior against precise predictions. Once again, no clear deviations have appeared. But the field is young. Each new detection adds clarity. What is striking about all these searches is their tone. There is no urgency, no desperation. Physicists do not expect confirmation tomorrow. They build experiments that listen carefully over long periods of time for small discrepancies. This is because higher dimensions, if they exist, are not expected to be dramatic intrusions. They are expected to be structural. Think of how the curvature of Earth was inferred. Sailors noticed ships disappearing hull first over the horizon. Surveyors measured angles. The evidence accumulated slowly through careful observation, not sudden revelation. Higher dimensions would be similar. They would bend behavior gently, not shatter it. There is also a philosophical shift embedded in this approach. Physics no longer assumes that reality must be directly observable to be real. It accepts that the universe may contain layers of structure accessible only through inference. This acceptance does not weaken science, it strengthens it. It demands rigor. Predictions must be precise, alternatives must be considered, models must earn their place through consistency and explanatory power. Higher dimensional theories survive not because they are exotic, but because they are coherent. Still, it is important to acknowledge limits. It is possible that higher dimensions exist at scales forever beyond experimental reach. If so, they may remain mathematically compelling, but empirically silent. Physics would then face a boundary, not of imagination, but of access. This would not be unprecedented. Certain aspects of the universe may simply be too remote, too subtle, or too energetic to probe directly. But even in that case, the pursuit is not wasted. The attempt to detect higher dimensions sharpens our understanding of known physics. It refines experiments. It deepens cosmology. It forces clarity about what we mean by space, time, and force. In science, even unanswered questions are productive. There is also something calming in the realization that discovery does not require spectacle. The universe does not perform for observers. It exists on its own terms. If higher dimensions exist, they have existed quietly for billions of years. They are not waiting to be found. They are simply there. And perhaps that is why detection, if it happens, will feel understated. A slight anomaly in data, a persistent deviation, a mismatch that refuses to go away. A whisper. As you rest now, it may be soothing to imagine scientists listening carefully to the universe, not demanding answers, but attending to patterns, adjusting instruments, refining questions. Reality does not hide out of malice, it hides out of scale. Some truths are too large to grasp directly, others are too small. Higher dimensions may be both. And as we approach the final stretch of this quiet journey, one last question begins to settle into place. If higher dimensions remain hidden, subtle, and perhaps forever indirect, Then what does that mean for you? And how should the possibility of unseen structure shape the way you think about your place in the universe? That is where our exploration gently turns next. Part 15. Living inside an incomplete view. You do not need to see every dimension to belong to the universe. Just as flat beings would live meaningful lives without height, your experience remains whole even if reality extends beyond it. Higher dimensions, if they exist, do not diminish your place. They deepen it, reminding you that the cosmos is larger, calmer, and more intricate than any single perspective can hold. It is natural, when encountering ideas like higher dimensions, to feel a quiet tension, a sense that if reality is larger than you can perceive, then perhaps your experience is somehow lacking or incomplete. But physics gently suggests the opposite. Incompleteness of view does not imply incompleteness of existence. A two-dimensional being would still love, wonder, and build a world worth living in. Height would add context, not value. Your life unfolds within the dimensions you can access, and within those dimensions, it is fully real. Science often reveals that what feels fundamental is actually local. The ground beneath you feels solid, yet it is mostly empty space. Time feels steady, yet it bends and stretches. Space feels flat, yet it curves. Each discovery does not erase experience, it reframes it. Higher dimensions, if they exist, follow this same pattern. They do not take anything away from the reality you inhabit. They add depth behind it. There is something quietly comforting in this realization. You are not required to perceive the entire structure of the universe in order to participate in it. You never have been. No one does. Even now, you live inside layers of reality you do not consciously register. The electromagnetic spectrum extends far beyond visible light. Neutrinos pass through your body unnoticed. Quantum processes shape every atom you contain without announcing themselves. Your awareness is selective by necessity, not by failure. Physics does not expect you to feel higher dimensions any more than it expects you to feel the nuclear force directly. It simply asks whether the universe might be larger than sensation suggests. And if it is, that largeness is not a threat. It is an invitation to humility. Throughout history, each expansion of perspective has followed a similar emotional arc. At first, the idea feels unsettling. Then, gradually, it becomes normal. Earth is not the center. The sun is not unique. The galaxy is one among billions. Each time, meaning does not vanish. It relocates. Meaning moves from position to participation. Higher dimensions, if they exist, do not relegate you to insignificance. They situate you within a broader order. You become not a mistake in a chaotic universe, but a natural outcome of a deep, structured reality. There is also something deeply peaceful about the idea that reality does not reveal itself all at once. It unfolds in layers, accessible at different scales, through different tools. Some layers are felt, others are inferred, others may remain forever abstract. This does not make them less real. It makes reality richer than immediacy. Consider how much of your own life exists beyond direct perception. Memories shape you even when you are not thinking of them. Relationships influence you across distance and time. Future possibilities affect present choices. Much of what matters most is not visible in the moment. Higher dimensions may be similar, present without being intrusive, influential without being loud. There's also a quiet ethical lesson embedded in this view. If reality extends beyond what you can see, then certainty must soften. Confidence must coexist with curiosity. Physics becomes not a conquest of truth, but a conversation with it. This attitude permeates the best science. Hypotheses are held gently. Conclusions remain open to revision. Models are trusted, but never worshipped. Higher dimensions fit naturally into this mindset. They are possibilities grounded in mathematics and motivated by unification, not articles of belief. You are not asked to accept them. You are invited to consider them. And consideration itself has value. It expands the mind's tolerance for ambiguity. It loosens the need for final answers. It encourages a sense of calm wonder rather than anxious control. Living inside an incomplete view is not a flaw of human existence. It is its condition. And yet, within that condition, there is astonishing clarity. You can understand enough to navigate, to build, to love, to rest. The universe does not withhold what you need. There is also something beautiful about the idea that the universe does not center itself on observers. It exists in full, whether or not it is fully seen. That independence gives it dignity. And paradoxically, it gives you dignity as well. You are not the measure of all things. You are a participant in something larger. That participation does not require comprehension of the whole, just presence. As you breathe now, your body obeys physical laws that may trace back to hidden geometry. Your thoughts arise from neural activity shaped by particles whose properties may depend on unseen dimensions. Your existence is already interwoven with structures you cannot visualize, and yet here you are, whole, grounded, enough. Higher dimensions, if they exist, do not pull you away from the present moment. They anchor it within a wider context. They remind you that calm is not ignorance, and mystery is not absence. The universe can be both understandable and unfinished. There is no obligation to solve it before resting inside it. Perhaps the most gentle conclusion of all this is this: the universe does not require you to see everything in order to belong. It has never required that. It allows you to inhabit one slice of reality fully, while other slices remain beyond reach. It trusts that this is enough, and it is. As this long, quiet journey through dimensions comes to rest, what remains is not confusion, but perspective. Not fear, but spaciousness. Not answers, but a sense of scale that softens urgency. The cosmos may have more directions than you can name, more structure than you can sense, more depth than any single theory can hold. And still, you are exactly where you need to be. Here, within this moment, within this dimension, at ease inside an unfinished view.